Hello everyone, and welcome to this last set of lectures in the course on embedded programming using C. And in this set of lectures we are actually going to be talking about some of the slightly less programming oriented parts of the course, but nevertheless very important from the point of view of the engineering aspects of what embedded design consists of. We are going to start by talking about safety. And what do we mean by safety in the context of embedded systems? In general, we can think about it or define safety in an embedded system as operating a system without causing unacceptable risk of physical injury or damage to the health of people, the environment or property. So, number of things to sort of unwrap over here. First is that there is clearly a system that we want to use. That is what we mean by operating. It is not an operating system, it is operating a system. Then there is also this interesting word here, unacceptable risk. And the important point over here is that you need to understand that pretty much anything that we do in reality has some amount of acceptable risk associated with it, right? The very fact that, sitting on a chair, you might have to accept the risk that there is a possibility you, slip off the chair and fall, right? You stand, you walk down the stairs, there is a possibility that you can trip and fall. Now the question is, have the stairs been made in such a way that the probability of somebody tripping and falling is high? In other words, are they very steep? Do they not have a railing? As long as there are some safeguards put in place, we decide that this is an acceptable risk. At some point we can say, okay, normal usage of this particular equipment should not result in any kind of damage or physical injury. And damage can happen in multiple contexts. It could be damage to the health of a person, the person who is using it, or other people who are affected by it. It could be the environment. The most classic example, of course, being nuclear reactors, which can pretty much destroy the entire environment in their immediate neighborhood. But even things like coal plants or other kinds of factories or other mechanisms which can have a fairly sustained and adverse effect on their surroundings. Or property. There could be physical damage directly to property as a result of the use of some particular system. Now, of course, we are talking about embedded systems. Does that really apply in the context of something like a nuclear power plant? The answer is yes, because a lot of what happens inside a nuclear power plant actually turns out to be controlled using some kind of embedded systems. And the focus is primarily on preventing accidents and mitigating hazards, right? You try and reduce the probability of a hazardous event occurring, right? And essentially define anything hazardous as something that could lead to harm. So this is our main purpose when we are sort of looking at the safety aspects of embedded systems. As you can imagine, there are two parts to this. One is in the design process itself, which means that as engineers you need to be aware of what are all the things that have to be taken care of over here and how you could possibly work around them, how you could design in a way such that the probability of error or of something going wrong actually reduces in the first place. Some of that will actually translate into portions of the code itself. It turns out that there are steps that you can take while writing your code that could actually improve the chances of having a safe by design system. So in general we use the term safety critical when you have severe consequences of system failure, right? The most obvious ones that you can think of would be medical devices. Now when we say medical devices, these could be of multiple types. One would be something like, let's say, a blood pressure monitor, or maybe the PPG meter used to measure blood oxygen saturation levels. Now those are important because the measurements that they give you are actually going to be play an important role in the treatment of the person, but they are probably not directly critical to the safety of the person. On the other hand, something like a pacemaker is absolutely critical. If a pacemaker fails, pretty much the person's heart may lose its rhythm of beating, right, and can have very severe effects on the health of the person. Now in the context of transportation, right, air traffic control is one of the best examples that we can think of. It's a very complicated exercise to keep several planes, especially in the neighborhood of an airport, all flying at the same time and in such a way that none of their paths are going to come close enough that they could potentially cause a chance of an accident. Industrial automation, right, especially in scenarios where you have conveyor belts where the item being manufactured is actually moving through, the goal is always to have these belts moving as fast as possible. You want to speed up the process of construction. Having said that, the kind of speeds at which things move on certain kinds of factory floors, any human being near it, if there is the slightest mishap over there, it could cause very serious damage to their personal health. And of course, power plants, areas where there are immense concentrations of energy, right, huge amounts of energy being converted from one form to another, and that very nature and the fact that it is being done under some kind of a controlled circumstance, and if there is the slightest loss in control over there, it can have very dramatic impact on the surroundings, on the plant, on even fairly distant areas if not contained properly. So these are what we call safety critical scenarios, right, where the safety of the system is absolutely paramount. You have to, you might end up having to sacrifice quite a lot of functionality that you might otherwise want just because the safety is more important. Now, what that means is that in practice, people end up coming up with a large number of standards for safety, right. So the first question is, why do we need standards, right? And the basic idea over there is that we need some kind of systematic design approaches, right? A way of approaching your entire system design that is based on experience, right? Best practices that have been learned from the experience of many engineers who have worked on this in the past. And essentially what we are trying to do is we are trying to distill ideas that are known to be good and work in practice, and see how we can make it such that it becomes easier for a new entrant into the design process to absorb these ideas and use them easily. There are many things that standards also permit, which is including something called interoperability. Whenever you want to have systems designed by different people or different groups or different maybe even departments of an individual company, to ensure that the parts can interoperate, you need to have some kind of standardized interfaces, right. So for example, as long as we can settle on the size of nuts and bolts that are used in a particular design, it means that the person manufacturing the nuts and bolts can just focus on getting them at the highest quality and the best possible output of those things, and all the others just have to design assuming that they have nuts and bolts of a certain size. And as long as you do that, certain size and strength, and as long as you do that, you can then make sure that there are certain guarantees that you can provide on the strength of the overall design that you are coming up with. Standards also make testing and validation a lot easier, and these are extremely important in the context of having large systems being built. So there are many kinds of standards that exist in practice. The International Standards Organization, or ISO, in fact, by its very name, you can imagine that it sort of specializes in the business of putting out standards, right. Among those, one particular standard number, ISO 26262, relates to road vehicles, and it basically talks about the functional safety of road vehicles, and there is a lot of information in this particular standards document which actually goes into detail on what kind of functional safety guarantees should be there when you are designing a vehicle that is meant to be operated on roads. Now, why would you do something like this? Once again, it becomes a question of anybody new who wants to build a car or a motorcycle or some other vehicle that is going to be there on public roads. As long as they are aware of these and they are able to say that these conditions have been satisfied, it becomes much easier for someone else to look at it and say, okay, these are good, this is a good design, because we know that all of these properties are automatically satisfied as long as it adheres to these standards. Similarly, there is also the International Electrotechnical Commission. This is more electronics specific, right? ISO is much more neutral. They even have things like standards for management. You have probably heard of the term ISO 9001 and so on, right? And or ISO 9000, which basically relates to the kind of processes that are used for managing various things in administrative departments, right? So it's not limited to electronics by any means, but there are a number of ISO standards that do relate to either engineering or even more specifically to electronic design. IEC on the other hand is pretty much mostly about electronics. For example, there is IEC 61508, which is functional safety standards for electrical, electronic or programmable electronic systems, right. Most electronic systems these days have some kind of programmable component, but there could be some that are purely electronic. There could be things like motors that are purely electrical. In each of those cases, there are certain standards which could be all the way down to how thick a wire should be or what kind of connector should be used in a certain context, right. But also applies in some cases to things like the design of software. What kind of guarantees can you provide in terms of how software is designed and how it runs? Similarly, airborne systems, avionics in general, aviation electronics have a number of different standards associated with them, and all of these are extremely important because these are systems which, if they lose control in some sense, are very difficult to recover. A car at the sort of worst case scenario, not worst case scenario, but you always have the at least a chance of just being able to pull over to the side of the road and stopping. In the case of a plane that is up in the air, if you lose control over it, then there's really very little that you can do, right. It just pretty much is going to be a very bad crash. So avionics in general has a lot more stringent standards of safety associated with it. Cars, however, especially given that cars are operating at higher and higher speeds these days, also have very strong safety requirements associated with them. So there are a number of other things that sort of come up in this context. One of them is the process of risk identification itself, right? How do you go about identifying the possible risks that can occur in a system? And there are systematic approaches once again that have been proposed over here. One of them is called FMEA, the failure modes and effects analysis. And effectively the idea that you are trying to do over here is, can you list possible failure modes of a system and quantify the effects corresponding to those failure modes, right? So can you detect a failure mode? In this case, what they try to do is assign a severity number to it, which is basically trying to quantify it, right? I mean, how bad is it? Now this is not an easy thing to do in general, right? It relies on a lot of prior experience of how bad a particular event is or what kind of impact it has. But the goal of approaches like FMEA is to try and make these things as systematic as possible. So there would be things like, does it have an impact on almost like checklists that you can go through in order to say, okay, what kind of severity number should I associate with it? You also have a probability number, which is you can have extremely severe events but with a very, very low probability of happening. For example, in the case of a nuclear power plant, of course the highest severity event is always probably going to be a complete nuclear reactor meltdown, right? So, and it is impossible to completely eliminate the possibility of something like that happening. There is always a chance that something like that happens for various reasons that you could not have thought of, right? But by eliminating all the more likely scenarios, you reduce the probability of this happening to a point where it basically becomes acceptable risk. Without that, it is essentially impossible to build anything, let alone a nuclear reactor, right? And the other thing, of course, that you need to have that they do is also specify things like the probability of detection, right? You need to have something which basically says, okay, if at all an event occurs over here, there should also be some quick way of detecting it, right? And if you cannot detect it, for example, then you probably need to make sure that it gets a higher priority. There, as long as you can detect it early and try to take steps to sort of avoid it, then perhaps it is it can be given a slightly lower risk because there are ways of mitigating it quickly. Essentially, this is one of many different ways by which you go about doing this. So what you do is, once you have got all of this priority number, you once again come up with a set of actions or plans for how to deal with this kind of a failure mode, improve upon it, and then say, okay, now having taken this into account, maybe the probability of this particular event has now been reduced, or the criticality has been contained in some way, or the probability of detection has been improved in a certain manner. Once I have that, I need to iterate on this design until I am satisfied in some way that this is a good enough design that it can actually be deployed safely. So risk mitigation essentially refers to, yes, there is always going to be a risk of any system going wrong in some way. The only thing that we can ask is, how do I reduce the probability of that happening to the point where it either is so low that I need not worry about it, or if at all an event occurs, I'm able to get over its effects very quickly and without too much difficulty. Now, for example, in aerospace systems, as I said, since loss of control means that you cannot really do anything, you can't even move off to the side or land safely easily, they typically just invest in multiple flight control systems, right? It's worth the extra cost, even though having multiple systems in place just to deal with exactly the same scenario, right, will definitely incur extra cost. It pays off in the long run because in case of one particular component failing, you always have a backup that allows you to work even with a single failure, right? So redundancy is one simple way of sort of addressing the risk associated with the failure of a particular component. Fail-safe systems are a very important aspect of engineering design in general, right? What it says over here is, for example, anti-lock braking is something that is used especially in countries where during winter the roads can get very slippery. What happens over there is that if you press hard on the brakes, your brakes can lock. What that means is that your wheels stop turning, but then they just go into a skid. Your entire car starts skidding, and skidding is very dangerous because it essentially means uncontrolled movement across an icy surface, right? Now, what needs to be done in that case is very often something called pumping the brakes, where you essentially let the wheels rotate in small amounts while at the same time hitting the brakes to try and sort of get some kind of extra traction on the surface. And there are anti-lock braking systems that actually allow you to, which basically take over when they detect that the wheels are skidding or slipping slightly, and automatically go into a mode where they start pumping the brakes at a very high speed, faster than a human can do, and thereby give you fairly good traction, right? These are sometimes called electronic traction control, a related part of anti-lock braking systems. Now, this is great because it really makes a difference to your driving conditions on when you are on icy roads. However, what if the electronics fails for some reason, right? And what a fail-safe essentially says is, in case of the electronics failing, one of the things that should happen is at least the mechanical braking part of it should remain. In other words, the person should still be able to press the brake pedal, and just using hydraulics or some other mechanism like that, there should be a way by which the brakes will actually get in contact with the wheels and be able to slow the car down, right? So this is a fail-safe. It basically says that in case of failure of the electronics, it falls back to something which is essentially going to still continue working, right? Similar things could be there in the case of automated door locks. In case that the electronics that controls the access over there fails, you have to now decide, should the door fail open or should it fail closed, right? What that means is, fail open essentially means that if the power goes, all the doors open, which is probably not good for something like a bank vault. But on the other hand, in case it is a place where people are actually sitting inside the room and they need to get out once the power fails, it might even be safer to just fail open so that the people inside are not trapped. So all of these are situation dependent. You need to know about the scenario in which you are designing, and based on that you need to decide what is fail safe and what is the correct decision to take. There are a number of other recovery mechanisms. For example, watchdog timers, which we have already discussed, essentially can be used in order to reset the system and restart in case of lockup, that is going into an infinite loop or something else where the software becomes unresponsive. And graceful degradation is very closely related to the idea of fail-safe systems. Essentially an example of that would be that medical pacemakers, they might have complicated functionality, including trying to control the particular rate or even adapt to the kind of activity that a person is going through. But the most basic thing, even if the electronics fails, should be that some part of it which just keeps the basic cardiac rhythm going should remain operational. This is graceful degradation. If some part fails, the other parts still continue to work, but they don't completely fail and the system doesn't just stop working as such. There are other approaches and techniques as well, including error detection and correction, separation of the different units, isolation of possible failing components, and so on, all of which contribute toward the idea of risk mitigation. But overall, if you want to just summarize everything, one of the most important things is going to be regular maintenance and testing. At the end of the day, there is pretty much no substitute for this. You have to be able to have a mechanism by which you can actually test the system on a regular basis and do whatever preventive maintenance is needed to ensure that it works correctly. So what we are going to do is take a look at a couple of examples of where things have sort of gone wrong in embedded systems design in the past, right. One of them is what's called the Therac 25. Most of these are incidents that you can search up on the internet. There are fairly detailed articles talking about the history of these things and so on. The examples I am giving over here are primarily from are mostly related to embedded systems in some way or the other, either embedded microcontrollers or embedded control, but the basic ideas behind them are more generic, right. So, Therac 25 was a computer controlled radiation therapy system which came out in around 1982 or so, right. So, this is from a considerable amount of time ago, but already electronically controlled medical equipment was there at the time. Clearly, one thing you can imagine is that on the one hand, maybe the state of the art in terms of how to design software had not yet advanced to the level that we are at now. On the other hand, people were also used to directly working with the computers almost at the assembly language or the instruction level. So, they knew every bit of what a computer could do. So, the design at that point was necessarily limited in its scope, but that also meant that people took a lot of care in terms of how it was implemented. What ended up happening, unfortunately, was that the original design had mechanical control switches. At some point, this was changed over to software based control, but there were some race conditions that got activated as a result, right. Now, what exactly these are, it's probably worth reading a little bit more about the history of these articles. It's not something that I'm getting into detail over here. The important point is that a software related glitch, it was finally narrowed down to a software related issue, which unfortunately led to a scenario where you could end up having wrong behaviors. For example, it had something where you had to choose between an X-ray beam and a different kind of beam, and the X-ray should have been activated only once the target is already safely in place. There were scenarios in which it could have got activated without the target actually having been positioned properly. As a result, there were scenarios where patients received several times the safe radiation dose, and unfortunately, there are at least a few deaths that were linked to this particular incident. It led to a lot of further investigation, and eventually the particular devices had to be taken off the market, and the company had to sort of have a lot of investigations surrounding it. But the point is that by the time you have got to the stage where in some sense the system that has been designed over there is responsible fairly directly for the death of someone who was undergoing treatment, it becomes very stressful even for the people who are designing. It was clearly unintentional, but that does not excuse the fact that it actually went wrong, which is why safety becomes such a primary issue in the design of such systems. There is another multiple recorded incidents of something called SUA, sudden unintended acceleration, right? And this is a scenario that has happened in multiple cars over the years, especially since the introduction of electronic injection systems and control, right? And effectively, the problem itself is easy to state. It basically says that the car accelerates without explicit driver control, right? This could incidentally even happen in a mechanical car, right? For example, let's say that you press the accelerator pedal down, and for whatever reason the pedal does not come back up, it basically gets stuck in place, right? There could be a blockage, there could be some other reason by which essentially the pedal gets stuck. Now, usually in such cases you can sort of try hitting it or knocking it, and yes, it usually sort of shakes loose, which is why people are a bit more comfortable with the mechanical aspects of it. You can see what happens when you press the pedal, and if it gets stuck, you know that you need to sort of try and knock it loose and get it out of place. With electronics, things are a lot harder. You might find that the pedal has actually come back, but the car continues to accelerate. You are not able to control it anymore by even pressing the pedal or by hitting it or trying to sort of jar it loose or anything like that. There were multiple incidents of this all the way from around 1987 in the case of Audi all the way up to the present day. In the case of cars like Tesla, there were incidents. I mean, in some sense this is even more aggravated than for other cars, because pretty much everything over there is electronically controlled, right? And there have been cases that seem to have been related to unintentional control failures, right? And The most sort of severe variant of this was Toyota's incident in around 2009 to 2011, when they actually had to recall about 500,000 vehicles or so, or even more than that, right? Because essentially recall meaning that they have to bring them back to the factory and get the entire thing checked and replaced, and the whole thing undergoes a major revision of design. So these are all a couple of examples of highly critical safety related issues that have happened in the past. There are many more. You can pretty much just search around for them and you will no doubt find a very large number of such scenarios.